Thanks to Christoph, Jean, and Eric. Awesome. Okay, let's get started. Yep. Oh, there's Eric. Awesome. Okay, let's get started. Welcome and good morning, everybody, to today's thesis defense by Travis Berger. I want to say a special aloha and welcome to Travis's family, who's joining us here today in the IFA auditorium and traveled all the way from the East Coast to be here with us today. So as is custom at the IFA, I will start off with a little bit of an introduction describing Travis's path for graduate school to where he is here today defending his dissertation. Before I do so, I just want to briefly highlight how special it is that we are here today. So first, this is probably the first defense. This is certainly the first defense since the pandemic that we have here in the IFA auditorium. It probably also is the first one that got the approval from the UH provost to take place, which is this document here. So we actually have the approval from the UH provost to be here in person today for this defense. I want to say special thanks to Melissa, who's been organizing all this and being the bouncer back there in the room. And also Karen at the director's office for making this possible. I know it means a lot to Travis and to all of us. Okay, so as usual, as an advisor, when you prepare for an intro like this, you basically try to find out something about the student. And usually the way you do this is you go to the internet and you type in student's name into Google and you hit the I'm feeling lucky button. And if you do that, in the case of Travis, you get Travis's professional website, which is actually pretty good. So I expected perhaps something different, but that's where you're taken. So on Travis's website, we learned that Travis is, of course, an astronomy graduate student. He studies stars and exoplanets. We'll hear a lot more about this today. But we also learned a little bit about his path before coming to Hawaii. So he did his undergraduate degree at UNC Chapel Hill, where he grew up, and we'll learn a little bit, I think, about his early days also outside of in the courtyard today, later on. But we also learned further down about some of his hobbies: hiking, snorkeling, surfing, of course, the sort of things that IFA graduate students get into. But right after this, it says watching basketball, college basketball. And for those of you who know Travis well, they know that watching college basketball is a very important matter. And so I don't know much about college basketball at all, but apparently in North Carolina, it's all about this. And two teams playing each other, and if you look it up a little bit more carefully, you find all kinds of reasons why one team is better than the other, or the other one is so much better than North Carolina is so much better than Duke. I'm pretty sure Travis has some very strong opinions about which of these two headlines is correct. But just to show you and to illustrate you how much Travis cares about this, I thought I'd put up a quote from someone who shall remain anonymous, but I'm pretty sure Travis can probably figure out who it is. Which happened during a game that Travis watched while he was in Hawaii, where in the end, despite Travis's observance of all superstitions, including taking off his shirt for the last quarter, Duke just barely came out on top. In frustration, Travis punched his bed and broke it. He could only use one side of it for at least a couple of weeks after that. I'm pretty sure he told me. So, those of us who know Travis know he's usually very quiet and reserved, and doesn't get riled up much. But when it comes to college basketball, apparently that changes. So just keep that in mind in conversations later on. Of course, like many of our graduate students, Travis got a lot of adventures during his time here at the IFA. That included going to the beach, dressing up for Halloween in costumes that I'm too old to understand, becoming a professional surfer here in the middle, bottom middle, all of our graduate students do, getting sung to here in the top left. I don't know, there was some special event, I'm not sure. And in the bottom left, getting in trouble. I think this was in the streets of Japan with his fellow graduate students. So in addition to having a lot of fun during his time as a student in Hawaii, of course, Travis also did a lot of research. Of course, that's why he's here today defending his thesis. And his thesis research, as he'll tell us today, is mostly using data from the Gaia satellite. And so when I met Travis in 2017, one of my top priority research projects was related to Gaia. That I wanted a student to take on for a dissertation. But this was also somewhat of a risky project. As many of you know, the astronomers in the room, Gaia data is available for everyone in the world at the same time. So it's very competitive. Basically, the student, Travis, had to compete against the astronomy community all over the world at the same time by diving into Gaia. And so Gaia DR2 Day, which is the big data release, the very first big data release that was revolutionizing astronomy, happened on April 25th, 2018 at midnight HST. So here in Hawaii, we were basically in the worst place possible to dive into this data set very early, very quickly, and get results out. But that did not stop Travis. In fact, on Gaia DR2 Day, I was in California at a conference or some meeting. I got an email from Travis titled First DR2 Plots, and the email contained a bunch of plots using Gaia DR2 data that we had discussed previously that would be good to make when the Gaia DR2 becomes available. And if you look at the timestamp of the email, that email was sent about 6 hours and 43 minutes after Gaia data dropped. So Travis basically stayed up the whole night or got up really early, I'm not sure which one it was, to make these plots very quickly. And in fact, only a few weeks after that, we managed to publish the paper using these results and beat most of the other teams in the world, at least in our subfield, to the punch on that. So it was a risky project, but I think in the end, it paid off. Of course, as many other students, Travis also spent some time on Mauna Kea observing the telescopes. These are some pictures from an observing trip that the two of us, in fact, did using the SuperEarths telescope up on Mauna Kea. And combined using Gaia and the data that he obtained, he ended up publishing papers, of course, as most of our students do. Travis ended up publishing 5 first author papers in peer-reviewed journals, 2 of them from his 699 projects working with Andrew Howard and Anne Bosgaard and Rolf Peter Kudrycki, and then the 3 at the bottom, which are the main bulk of his thesis work. I just want to point out here that, as you see from the co-author lists from the bottom 3 papers, those include Eric and Jen, who are also committee members from Travis. So advising, I'm standing up here cracking jokes about Travis, but advising Travis was really teamwork, both with Jen and Eric, who invested a lot of time in this. So I want to thank them also for their contributions to this. Okay, of course, Travis went around and presented his work at conferences. Luckily, this was still possible before the pandemic for a little bit of time. So you see some images here up in California at the Kepler K2 Science Conference, and on the bottom right at KIGP in Santa Barbara. Early this year, Travis also participated at a AAS press conference. So the bottom left panel shows this. This is, of course, a Zoom screenshot. It was all online already. I picked this screenshot because, as you know, it actually highlights the little Zoom rectangle while Travis is talking. And I did this because Travis actually spent most of this press conference talking, because he got most of the questions from the reporters, which was really quite impressive. There were a lot of panelists up there, but most of the questions went to Travis, and he handled them really well. So it was a really nice moment. And of course, most recently, Travis's research was also recognized for the UH Student Excellence in Research Award, which is a very prestigious award that the university gives out to research students. Okay, and of course, Travis has chosen to stay in astronomy in the academic path. He has accepted an offer to become a NASA postdoctoral program fellow at NASA's Goddard Space Flight Center in Maryland, working with the TESS team. I know this was high on his priority list when applying for jobs, so we're all very happy that it worked out. And assuming that everything goes well, we wish him today, we wish him all the best with his job at NASA. And so with that, I will turn it over to Travis to tell us about his research. So I failed to mention at the beginning that, of course, the procedures here will be that Travis will be giving a talk. After that, we'll have time for questions from the general audience, both here and on Zoom, and then after that, we'll have a closed session with the committee. Thanks, Travis.
Great. Thank you for that great introduction, Dan. I'll go ahead and share my screen here. Okay, so I want to thank you all for being here today, both in person and then also online. So I'm going to be talking to you about the work that I've done over the past 6 years, which has been focused on the precise demographics of Kepler exoplanets in the Gaia era. Now, first I want to talk about a brief introduction about the Kepler mission. So the main goal of the Kepler mission was to detect Earth-like planets around Sun-like stars. And to do this, Kepler ended up staring at this one field of the sky, which I've highlighted here, which you can see is in the constellation of Cygnus, just above the galactic plane. And if we zoom in to this field and look at the actual Kepler detector, you'll notice that there are hundreds of thousands of stars located on the Kepler detector. And to detect these planets around these stars, Kepler ended up measuring the brightnesses of each of these points consistently over roughly 4 years. So to give you an idea of exactly what happens and how Kepler detects these exoplanets, if we then do some, for instance, if we see this video which shows 2 stars with different sized planets orbiting around them, you'll notice that over time the light stays constant until the planet passes in front of the star. And depending on the relative size of the planet to the star will then give us an idea of how deep that transit is. And so therefore, if we know how deep the transit is and know the size of the star, then we can start to learn a little bit of information about the size of the planet. Now, to give you an idea of exactly how many planets Kepler discovered over its 4 years, as of December 2017, Kepler had discovered over 2,000 planets, and this is just the plot showing the size of the planet relative to Earth on the y-axis versus orbital period here on the x-axis. And you'll notice that the yellow points here are those planets that were discovered by the Kepler Space Telescope, and that the majority of those planets are actually between the size of Earth and the size of Neptune. And now this is particularly interesting for scientists because we don't have any planets similar to those planets within our own solar system. And so therefore, this is definitely a point of interest for our eventual investigations. So as I mentioned before, to know the size of a planet, we must also know the sizes of stars. But as of roughly the end of 2017 or so, we did not know the distances and hence the sizes to the vast majority of Kepler stars. Now, you're probably wondering, well, why are distances important? Well, it turns out that without distances, it is difficult to tell the difference between a large star that is very far away and a small star that is close, because we receive similar amounts of energy from those stars. Now, fortunately, Gaia DR2 ended up dropping in April 2018, and with Gaia, this allows us, Gaia ended up measuring parallaxes to a large number of Kepler stars. And it did this by using something called a parallax. Now you can kind of get an idea of exactly how parallaxes work by if you hold up your finger in front of your face and then you blink your eyes back and forth, you'll notice how your finger moves relative to the background objects. And how much your finger moves will give you an idea of exactly how far away your finger is. Now, obviously, astronomers can't do that on astronomical scales. Stars are much too far away to use our eyes to determine the distances. So instead, we can use the distance or the size of Earth's orbit as our baseline to then determine the distances to stars. And so, for instance, if we measure some parallax of a foreground star and see how much it moves relative to background stars, that gives us an idea of how far away that star is. And so therefore, with these Gaia parallaxes, we can now infer the distances and hence the sizes of the vast majority of Kepler stars. So here is the way things looked as of 2017. This is some data from Mathur et al. 2017 showing stellar radii on the y-axis versus effective temperatures here on the x-axis. And we're at this point, we had median fractional radius precisions of about 25% or so. And this is just largely due to the fact that we did not have the distances to the Kepler stars. Now, how do things change when we implement Gaia DR2 parallaxes? Well, we see that things change pretty significantly. And in particular, with Gaia DR2 parallaxes, this allowed us to get down to median fractional radius precisions of about 8%, which is a factor of 3 or so better than what we were getting beforehand. Now, with this information, this actually allowed us to classify the percentage of main sequence dwarfs, which make up roughly 2/3 or so of the Kepler target sample. Another 21% are made up of subgiants, and then the final 12 or so % are made up of red giants. Now, you might notice that there appears to be a secondary main sequence of stars for cool main sequence stars. And this is just due to the fact that these stars do not evolve very quickly within timescales of the universe. And so therefore, these stars that are at such large radii are likely binaries because we're getting light from 2 stars instead of just 1. And then you'll also notice that there's a gap in the distribution of effective temperatures. And this is just due to the fact that we're using effective temperatures from previous work from Mathor et al. 2017, which used diverging effective temperature scales, which met at about 4,100 Kelvin. So, okay, now that we've got all these brand new stellar radii, what can we learn about the planet population that orbits these stars? So here is the way things looked before Gaia DR2. We've got our planet radii on the y-axis here versus incident fluxes on the x-axis relative to how much Earth receives. In red are our confirmed planets, and in black are our candidate planets. And you'll notice that there don't appear to be any super sharp features going on in this diagram. And in general, for planets smaller than about 4 or so Earth radii and between 1 and 4 or so, there's just kind of a big blob of planets here. Not too much definition. Now, how do things change when we implement Gaia DR2 parallaxes? Well, things sharpen up very nicely. And I'm going to flip back and forth once more. And what you'll be able to see here is that there appear to be 2 populations of planets. One are the SuperEarths, somewhere between 1 and 2 or so Earth radii, and then another population of what we call SubNeptunes from about 2 to 4 or 5 or so Earth radii. Okay, so another thing we can find from this plot is that there is a gap in the distribution of planet radii, which you can see circled here. This is detailed in Fulton et al. 2017, and I'm going to go into the details of this a little bit later, so stay tuned. We can also update the census of planets within the habitable zone. So these are planets that might, for instance, harbor life, because this is where they can actually have water in liquid form. So we update the census with 34 confirmed and 109 planet candidates within the habitable zone. And then you might also notice that there appears to be a clear inflation trend going on for Jupiter-sized planets. And now these planets are massive enough to hold on to their atmospheres. And so instead of losing their atmospheres when they receive lots of energy from their host stars, all of that energy goes into puffing up their atmospheres. Okay, so I think we can all agree that these revised radii are great, but we do want to know additional information such as the masses and ages of Kepler stars. So here is what the data looked like back in 2017 again. This is isochrone modeled stellar radii and effective temperatures from Mathor et al. And what happens when we, for instance, determine more detailed stellar properties and use a model grid? Well, with Gaia DR2 parallaxes, well, we see that things do change. In particular, you'll notice that there's kind of brighter colors in this region of the diagram that are more subgiant stars, as we found based on the Gaia DR2 parallaxes. We also see a much better defined red clump. And to give you an idea of exactly how we created this plot, we used a combination of input G and K photometry, Gaia DR2 parallaxes, and then spectroscopic metallicities for Kepler stars wherever we had them. These comprise roughly a third or so of the stellar sample shown here. And then to actually determine the detailed physical parameters, we used a custom mist interpolated grid, which used spectroscopic metallicities ranging from -2 to 0.5 dex and 0.05 dex steps, and then ages which range from 0.1 to about 20 gigayears in a log linear form. And all in all, this creates a grid of roughly 7 million models. Now, you might be able to notice that there no longer appears to be a binary main sequence going on here for cool stars. And this is just due to the fact that we are actually fitting our empirical data with the isochrones to the isochrone model grid. And so therefore, these models actually do not grow to such large radii within timescales of the universe, or even within 20 gigayears, because these stars are less massive and do not burn through their fuel as quickly or evolve as quickly in this diagram. And in addition, you'll notice there's no longer an effective temperature gap occurring for cool stars. And this is just due to the fact that we're using this sort of uniform scale of G minus K photometry to determine effective temperatures. And what I want to stress is that we've got masses, ages, densities, and more for every single star within this diagram. Okay, so we've got all these great stellar properties. Now what can we learn about the planets? So before I go into the details of exactly what we've determined here, I want to take a step back and talk a little bit about some of the theoretical underpinning of the planet radius gap, which is detailed in Fulton et al. 2017. This plot shows the number of planets per star or occurrence rate on the y-axis versus planet size on the x-axis. And what you'll notice is that there is an underdensity of planets located at about 1.8 or so Earth radii. This is what we call the planet radius gap, which separates the SuperEarths at about 1.3 or so Earth radii from the SubNeptunes up at about 2.4 or so Earth radii. And that this discovery was made possible thanks to the very precise stellar properties of the California Kepler survey. Now, this gap has been the subject of a lot of additional follow-up work. And so people have started asking questions such as how the gap varies as a function of incident flux, orbital period, stellar mass. But I think in particular, looking towards the future, stellar age might be an interesting region to check. And that's something that I'll be talking about a little bit later on in this talk. Now, we need to come up with some sort of a mechanism that can create this gap in the distribution of small exoplanets. So I'm going to go through a few of them now. So I'm going to be talking about two of the major competing theories. The first of which is photoevaporation, which uses very high energy XUV and EUV radiation, usually within the first 100 or so million years of the host star's lifetime, to strip planet atmospheres. And so if we actually look and see how this photoevaporation might affect planets within this sort of region of parameter space, I'm going to show a little bit of a mini simulation here. So here is a plot from Owen 2019, which ended up talking about atmospheric escape of exoplanets. And the key thing to note on this plot is that we've got our mass loss timescale on the y-axis. We've got our atmospheric mass fraction here on the x-axis. So you can kind of think about that as how much mass is in the atmosphere versus how much mass is in the planet as a whole. So if we, for instance, start off with a planet that's at point 1 here, you'll notice that it is currently above this sort of mass loss timescale. And so this is set at about 100 million years, which is roughly the timescale that photoevaporation is expected to act. And so over time, if we were to evolve that planet forward, it wouldn't really lose very much of its mass because this curve is actually above this mass loss timescale when the planet is essentially, the mass loss timescale is therefore shorter than the amount of time that the planet would need to lose its atmosphere. And so therefore it's actually stable to losing its atmosphere from photoevaporation and might just cool and contract and become, for instance, roughly a sub-Neptune sized planet. However, we can end up with another situation where, for instance, if we have a less massive core of the planet, or it's at a smaller separation, or some combination of the two, you can actually increase the overall mass loss timescale, or shift this red curve down to the point where if you start off with a planet that's at roughly 1 year, because all of this red curve is pretty much below, you would then end up resulting in this sort of runaway mass loss of the atmosphere, which would then place this planet at roughly a super-Earth size and be left with no atmosphere whatsoever. Okay, so that was photoevaporation. Now I want to talk a little bit about core-powered mass loss, which uses a combination of the heat from formation, the energy in the core left over from its heat from formation, from core accretion, for instance, in combination with the bottleneck luminosity from the host star to strip planet atmospheres. Now, this is expected to act on timescales of roughly a gigayear or so because it's more dependent on, for instance, the bolometric luminosity from the host star instead of it necessarily being focused on the XUV and EUV radiation of photoevaporation. Now, to go into some details of exactly how core-powered mass loss might actually act on the planet population, again, I'm showing this plot from Fulton et al. 2017, but now if I show this diagram from Misner and Schlichting 2021, I'm going to go through the details of this point by point here, but if we start off with some planet that's in a gaseous disk, the gaseous disk then dissipates, and then that planet will end up losing that sort of support from the pressure in the gaseous disk, and then it will spontaneously lose a decent amount of mass at the beginning. But it will then follow one of essentially two major tracks, and this is dependent on whether or not its mass loss timescale is shorter than its cooling timescale. And so, for instance, if the cooling timescale is shorter, then the planet can effectively cool And this is usually based on how much energy is in the core versus how much energy is available in the atmosphere. And so if your core energy is dominated, this is a situation where you'd actually have atmosphere energy is greater than that's left over in the core. And so you'd end up with efficient cooling and little further loss. And you'd end up with an atmosphere of roughly a few percent, which would place it at roughly 0.2 here in that sub-Neptune peak. Now, if we have the opposite situation where essentially the core has a lot more energy than the atmosphere, then your sort of mass loss timescale is then shorter than your cooling timescale. And so therefore you can end up losing a significant portion of your atmosphere after that point. And you could end up with one of two situations based on this most recent work of core-powered mass loss. You could end up either with a situation of 3A, which is that the planet ends up retaining a thin hydrogen-helium envelope because the planet might eventually be able to cool faster than losing the rest of its additional atmosphere. Or you could end up with a situation of 3B, where essentially your entire atmosphere is lost and your cooling timescale still remains longer than your mass loss timescale. Now, given all of this information here, this might actually give us a slight idea of which sorts of these situations are more common than the others, especially given the relative heights of the peaks and the sort of depth of the gap. Okay, so now that I've talked about the theoretical underpinning of exactly how we create the planet radius gap, now I want to see exactly how these theories predict and how they compare to the observations. So here I've got the models from Owen and Wu 2017. We've got planet radius versus orbital period here. And darker colors in this plot indicate higher densities of planets or higher occurrences of planets. And on the right, we've got our observations from Fulton et al. 2017. And what you'll notice is, at least looking at the colors, in general, the darker colors match up to where the darker colors are found in the observations, in both the models and the observations. So again, you see qualitative agreement between the models and the observations. Now, if we take a look at core-powered mass loss, again, we've got our models over here on the left, which come from Gupta and Schlichting 2019. And we've got our observations on the right, which show Fulton and Pettigura 2018's work. And you'll notice again, in general, the darker colors match up with the darker colors in both of these plots. And so the models match the observations. So you're probably wondering, well, how do we go about differentiating between these two theories if both have described the observations pretty well so far? And so you might be able to think about a few different avenues that we could take. You know, we might want to, for instance, look at a larger sample of planets. We might, for instance, want to have more precise stellar and planet properties, or we might want to look at other areas of parameter space. And so when we kind of combine a few of those things together, I've plotted here planet radius on the y-axis versus incident flux on the x-axis. And now the points are colored according to the stellar mass of the host star. The solid points here are confirmed planets, and the translucent points underneath are candidate planets. And if you've got a particularly keen eye, you might have noticed that there appears to be a general color gradient going from left to right on this plot. And if we to first order assume that planets are on roughly similar orbital periods around different mass stars, then higher mass stars will have higher luminosities, and therefore the planets that orbit those stars will receive higher amounts of incident flux. So that's to first order why we see this overall gradient. Now, things are more complicated than that, but for this, it suffices. Now, you might notice that there is an underdensity of planets located in the central region of this plot. This is what we call the planet radius valley, which is essentially a two-dimensional representation of the planet radius gap. And you'll notice that it has a little bit of a slope, and that it also separates the populations of SuperEarths and SubNeptunes. Now, this slope indicates that the planet radius valley might actually depend on things such as the incident flux that that planet is receiving. And given the relationship between incident flux and stellar mass, we would also expect to see a similar relationship between the planet radius valley and stellar mass. But for now, I'm going to want to go to another area of parameter space, which is how the planet radius valley depends on stellar age. So here I've plotted the number of planets on the y-axis versus planet radius here on the x-axis. Each of the ticks that you can see down here at the bottom show the individual planet radii that make up this purple histogram, which represents the old planets, or planets that have stars that have isochrone ages greater than about 1 billion years old. Now you'll notice that there are two peaks. one of which corresponds to the SuperEarths and the other of which corresponds to the SubNeptunes. SuperEarths are defined as any planet between 1 and about 1.8 or so Earth radii, and a subNeptune is any planet between 1.8 and about 3.5 or so Earth radii. And so if we do some simulations and count up the number of planets that are in the SuperEarth bin and the number of planets that are in the SubNeptune bin, and based on the uncertainties in the planet radii, we can determine this overall ratio, which is the ratio of SuperEarths to SubNeptunes. And unsurprisingly, given the peak of these, the relative heights of the peaks, this ratio is roughly 1. Now, okay, this is the way things look after a gigayear. Now, how do things look before a gigayear, or for planets that are younger than about a gigayear old? Well, we see in green here that the SuperEarth peak in particular is significantly lower than the SuperEarth peak in the old planet distribution, and that the SubNeptune peak is significantly broader than what we see in the old planet distribution. Now, if we do a similar calculation and add up the number of SuperEarths and the number of SubNeptunes and then divide, we get a ratio of 0.61 plus or minus 0.09. So this represents an actual 3 sigma difference between the number of SuperEarths and SubNeptunes between old and young planets. So what exactly does this suggest? Well, I think it suggests that SubNeptunes are becoming SuperEarths on roughly gigayear timescales. Now, this is one of the first times we've been able to put an exact timescale to this sort of radius evolution of planets. And originally we thought, oh, this might be indicative of core-powered mass loss, given that it's expected to act on roughly gigayear timescales. Now, some recent work by James Rogers and James Owen has actually shown that photoevaporation can reproduce similar results on gigayear timescales. So we're going to need something else to differentiate between those two theories. Okay, so I've talked a little bit about one of the big results, which is stellar age and how the planet radius gap depends on stellar age. Now, what else can we actually learn about the planet population? So again, I'm going to take you back to this plot of planet radius versus incident flux. And now I'm going to focus on a region of parameter space that I haven't talked about before, which are planets within the hot sub-Neptunian desert in this dashed box. So originally it was expected that we wouldn't find any planets within this region of parameter space. So let's zoom in and see exactly what's going on with these guys. So here on this plot, I've got the low flux planets shown over here on the right in gray. But I really want you all to focus on the left-hand region of this plot, which shows the high flux planets. On top, we've got our high flux sub-Saturns, and on bottom, we've got our high flux super-Earths. And in the center here, we've got our desert planets. Now, you might have noticed that there are little black bars attached to each of the points here. And these black bars actually represent the overall incident flux evolution that that planet has experienced throughout its lifetime. And so if we were to, for instance, evolve the star back to its zero-age main sequence, that would be roughly how much flux that planet would be receiving, assuming that its star was at the zero-age main sequence and that the planet was at roughly the same orbital period. Now, you'll notice that most of the planets that are located here within the hot sub-Neptunian desert have actually only recently shifted there due to stellar evolution. And so this might actually be a reason for why these planets can be here. If photoevaporation is expected to be the main mechanism for which these planets will lose their atmospheres, then when their stars were very young, these planets weren't receiving quite enough incident flux to truly lose their atmospheres. And so they've only recently shifted there due to stellar evolution. But there are 9 planets that have been within the hot sub-Neptunian desert for their entire lifetimes based on this analysis. And so therefore, we need to come up with some sort of other reason for how these planets exist. And that will be the subject of future work. Now, in addition, I kind of want to point out this other region of parameter space where we find some cool inflated Jupiters. As I mentioned before, I talked about hot inflated Jupiters, planets that were receiving large amounts of incident flux from their host star. But we shouldn't expect for planets to be inflated at these sorts of incident fluxes, which are roughly on the order of how much flux the Earth is receiving. So here we've got planet radius on the y-axis versus incident flux again on the x-axis. And the points here are colored according to the stellar age of their host star. And you can see actually where each of the host stars for each of these points are located in this inset diagram in the upper right, showing stellar radius versus effective temperature. And what I want you all to focus on is this red kind of horizontal line in the bottom region of this plot, which represents roughly the maximum radius that we would expect for one Jupiter mass pure hydrogen helium object at roughly the age of Earth. So any points that you see that are significantly above this line need to have some sort of an explanation for how they are so inflated. Now you'll notice that there's Kepler 706b and then also Kepler 468b, which are more than 1 sigma above this line. Kepler 468b, according to its color, appears to have a relatively young age. And then also it has been circled in red, and then it's also got this orange square around it, which indicates that it has other indicators of use, such as UV excess flux relative to its volumetric luminosity and rapid rotation. And given all of these factors, we might be able to say that Kepler 468b might still be relatively young and still cooling and contracting from its initial formation. But there's no such easy explanation for Kepler 706b, which you'll notice is in yellow here, which indicates that it's older than the age of the universe. Now, that's not technically physical, so what is the reason for this? Well, we've actually been able to follow up this object with some AO imaging, which has indicated that it does have a stellar binary companion, which can artificially inflate the age that we might derive for that star. And so therefore, Kepler 706b is going to be the subject of future work as well. So finally, I want to go into some of my past and also some planned work that I have with stellar ages. So here I'm showing a plot of stellar radii versus effective temperature, and this is for the Kepler planet host star sample. The points here are colored according to their maximum age uncertainty, where darker colors indicate lower uncertainties and lighter colors indicate higher uncertainties. And you'll notice that in general, isochrone ages are pretty precise because of the low uncertainties in this upper left-hand region of the diagram. And this is unsurprising because these are more massive stars. And they move through these sorts of regions of parameter space very quickly because they burn through their fuel more quickly. Then we've got these other regions of parameter space where isochrone ages are not quite as useful and in some cases very useless. And so, for instance, for stars down on the main sequence, as I've mentioned before, these stars do not evolve quick enough within the age of the universe to grow to any true extent, at least in these sorts of diagrams, for isochrones to be able to determine their ages. And so therefore, isochrone ages aren't very useful for these stars, the M dwarfs and K dwarfs. But you'll also notice that I've circled the giant branch here. And the key thing about the giant branch, you'll notice that it is a combination of different colors, but it's very important to have exactly where the giant branch occurs, as well as very, very well-determined effective temperatures and metallicities to truly get both the mass and age of a giant star. And so therefore, we caution about necessarily using these isochrone ages that we've determined for those stars. Now, also, I want to caution a little bit about some old edge of grid models, which occur kind of close to the edges of the models that we actually have, that we try to fit with our observed data. And this is just due to the fact that these points are usually forced down onto the grid of models, and so therefore their parameters are usually somewhat unreliable. Okay, so just to kind of take you through exactly what sorts of age indicators are optimal in different regions of the HR diagram, you won't be surprised that isochrones are very effective in this upper left-hand region of the diagram. Another age indicator that I want to talk about is lithium abundance, which I've actually done a little bit of work on in a project that I did with Andrew Howard and Ann Bosgaard in my first year here. So on this plot, I've got lithium abundances, which are plotted on the y-axis versus effective temperatures here on the x-axis. This is of the red points are Kepler planet host stars from the California Kepler survey. And in blue, I've actually shown an empirical isochrone for the Hyades cluster, which comes from data from Bosgaard et al. 2016. And this represents an age of roughly 650 million years. Now, lithium abundances can be used as age indicators because stars are expected to start off with roughly the same similar lithium abundances and then burn through that lithium over time. And so, for instance, we can use this overall curve here to then say any stars that are above the Hyades curve in blue here are relatively younger than the Hyades, while those below might be older. Now, you'll also notice that there's a strong effective temperature dependence here. And this is just due to the fact that it turns out that cooler stars have deeper convective envelopes. And so therefore, the lithium is convected deeper into the interior where it's much hotter and it's burned more quickly. So when we put all of this together and take a look at the planets that orbit these stars, here I've shown the fraction of planets on the y-axis versus planet radius here on the x-axis. In the green histogram, I've shown planets that are younger than the Hyades. And in purple, I've shown the planets that are older than the Hyades. And what you'll notice is that there are many more subNeptunes in the young bin, which matches up with the sort of observations that we had with the isochrone ages that I showed a little bit beforehand. So that's good to see that we are seeing agreement between different age indicators here. In addition, so if we're thinking about optimal age indicators at various areas of the HR diagram, astroseismology is typically very effective on the red giant branch, especially when you can do detailed frequency modeling. UV excess can be pretty useful for solar-ish type stars early on in the main sequence when they're still young and very active and they produce a lot of excess UV flux. Rotation can also be used for a large number of stars throughout the main sequence, from roughly solar type all the way down to M-ish type stars. And the whole idea behind this is stars start off young and active. They've got these convective envelopes, which then essentially allow them to spin down and lose angular momentum over time. And then kinematics can also be used to determine the ages of ensembles of stars, but usually this is a pretty rough age indicator. And so when we put all of this information together, we can see how many Kepler planet host stars have all these different age indicators. And you can see each of the colors here represent a different age indicator for that particular star, and that there are actually some of these points here that have multiple age indicators. Now, the actual star points on this diagram are particular stars that I followed up with my thesis observations. In particular, Kepler 2 to see whether or not those stars have any, for instance, binary companions, and SuperHDS to measure additional lithium abundances and also potentially find spectroscopic binaries to really get robust ages for those stars. And so the whole idea here is to combine all of these age indicators together to do a full analysis of the ages of Kepler stars based on where age indicators are most optimal. And then I also want to talk a little bit about some applications to K2 and TESS with Gaia DR3. So Gaia DR3 dropped in December of 2020, so just about half a year ago. And so we can actually use all these brand new parallaxes as well as the photometry from Gaia DR3 to do a joint analysis of Kepler, K2, and TESS stars. So here I'm again plotting stellar radius versus effective temperature. In gray underneath is just the Kepler sample that I've shown you today. And in blue is the combined Kepler, K2, and TESS sample that I'm proposing to focus on for my postdoc. What you'll notice here is that the vast majority of Kepler stars are of the F, G, and K type stars. And so therefore, when we end up adding K2 and TESS data to this overall sample, we end up seeing that there's a significant increase in A-type and M-type stars, which will then give us a broader range of stellar masses to then analyze the properties of planets. And to give you an idea of exactly how many planets we would be dealing with if we combined all this information together, you can see here in gray is what we were dealing with Kepler, and then with the combined Kepler, K2, and TESS samples, we're roughly doubling the exoplanet sample that we had to analyze. So with all of this information, this then will allow us to, for instance, truly investigate some of the things I've talked about here today. So for instance, what's going on with planets within the hot sub-Neptunian desert, which TESS and K2 have found a few planets within that region of parameter space. So those could be some interesting avenues there. To determine whether or not there are any planets within the planet radius valley. How empty is the valley? And so this sort of additional data might actually give us a better idea of that. In addition, we might want to know, for instance, the valley's dependence on things such as stellar mass and age, and the broader range of masses and types of stars with K2 and TESS will really give us a little bit more leverage there to potentially differentiate between theories such as core powered mass loss and photoevaporation. So with that, I want to leave up this quote, this sort of scenario that Dave Soderblom talks about in his 2010 review of stellar ages. So if we discover a planet with a biosignature, one of the first questions we will ask is how old is that system? And so therefore, I think a lot of my thesis work has gone into answering that question, and I hope will be useful for the future. So with that, I want to put up my acknowledgement slide and take some time to thank all of you that are here, as well as some particularly important people. I want to thank my advisors, Dan, Jen, and Eric, for all of your help throughout my entire thesis project, from the proposal to looking over papers and providing comments to scientific investigations, all that sort of stuff. Thank you so much. I want to thank my thesis committee members, Jean and Christoph, for providing help with both observations and then providing additional feedback at various thesis committee meetings. I want to thank my previous advisors, Rolf, Andrew, and Anne, for all of your help on my various 699 projects. And I'm very happy that we were able to get papers out of those projects. I want to thank my faculty mentors, Duncan and Ben, for being there for me to talk about things that aren't necessarily science related and provide some maybe soft help with soft skills. I want to thank Teru, Adam, and Mauna Kea observatories and personnel for all of your help with all of the observations that I was able to take throughout my thesis. I want to thank my roommates, Sam, Ben, and Esson, for putting up with me over the past 6 years and all of my screaming during Carolina basketball. I want to thank my classmates, Maisa, Christian, ZJ, Denise, Xiao, and Ja, for all of your help throughout, especially the first 2 years, but then throughout my dissertation as well. I want to thank all the members of the Huber Research Group, which has grown to be pretty large throughout and had many different people over the years: Eliza, Connor, Munshri, Casey, Erica, Ashley, Dan, Mark, Nick, Miriam, Jamie, Lauren, and Jing Wen. Thank you for just being able to look over my plots and provide feedback at various group meetings and ask great questions. Thank you for IFA Splat as well, for providing feedback on various research topics. And then I also want to thank the IFA graduate students. If I have not yet mentioned you, thank you all for being there for me over the past few years, especially honorary IFA grad student Jeff Schuler. I want to thank the IFA postdocs as well for all the sort of help that you've provided and fun times. I want to thank the IFA staff for all of the help with logistics of either travel or anything else, protograd visits, all that sort of stuff. And I want to thank Melissa, Kurt, Gavin, Raja, Bill, and CSRS for helping make this in-person thing happen. I want to thank, and then also for all of the technical sort of side of both setting this up and then throughout my dissertation. And then I also want to thank my friends and family, and in particular, my parents, Todd and Tracy, my brother, Tyler, and my partner, Katie, for all of your support over the past 6 years. You've been my rock, and I really appreciate you listening to me talk about science and being interested in it. So with that, I'm going to put up my summary slide, and I want to thank you all for your time and ask for any questions.
Excellent, thank you, Travis. So as I mentioned at the beginning, we'll now have some time for questions, both here in the audience and online on Zoom. So I think I'll start in the room here, and then I'll ask Kurt to help me navigate any questions that might be on Zoom. So any questions here? Yes.
So Travis, with the new EDR3 and including the test planet sample in K2, there's a lot more A and M stars. Are the current methods of calibrating those with ages, the isochrones and the lithium lines, are those going to be appropriate for such a large number of samples that we're going to see there? So
to talk about like isochrone ages will be useful for A-type stars. In particular, because they move pretty quickly across the HR diagram, so we can get at least more precise ages for those stars. Now, lithium abundances might not be quite as useful for M-type stars, largely because they burn through their lithium abundances so quickly, because they have such deep convective envelopes that you'd have to find very, very, very young N-type stars for that to work. But that's not to say that there aren't necessarily some stars within, K2 and TESS that would have those sorts of parameters. So yeah.
Okay, any more questions? Yes, Mike.
For the age dependence of the planet radius depth, box number 3, you chose this 1 gigayear bin line to basically divide the unknown. How would you do this if you wanted to remove sort of an arbitrary choice of age?
I gotcha. Yeah. So so to remove an arbitrary sort of choice of age, I mean, something that you could do, for instance, is look at plot stellar age and then planet radius as a function of just in general stellar age, and maybe determine, for instance, the have some sort of a KDE or some sort of a representation of the points and the density of those points, and see whether or not you actually see any sort of radius evolution as a function of stellar age. Unfortunately, so that was something that we actually tried with our work, but given the relatively small sample sizes that we were dealing with, I mean, we're talking about, I think there was roughly like 40, I think it was like 90 or so planets per histogram bin or something like that, at least for stars that had relatively good isochrone ages. We're mostly focused on kind of F-type stars and in that region of the HR diagram. And so, yeah, that if we were to, not do some sort of arbitrary choice of age, plotting age, stellar radius versus age would be a thing that we could do.
Ben.
Since Mike stole my first question, I'll go on to the second one. What's the prospects of increasing the number of planets on plot number 3, on histogram number 3, such that you can make more planets?
Okay, so yeah, so increasing the number of planets on plot number 3 here. So the idea is, both with K2 and TESS, you're going to have a larger, just larger planet samples, right? Like we're going to be dealing with and determining the ages of those stars through Gaia EDR3 parallaxes. So the idea is run Gaia EDR3 parallaxes as well as Gaia photometry through a lot of the sort of pipelines that I've already produced, and then determine the ages of those planets through that way, and then that will then increase the number of planets that we could potentially add to that plot. Now, K2 and TESS are definitely looking at different areas of the galaxy as well, and so you're going to be probing different ages and that sort of stuff. And so any stars that would potentially have planets that are, for instance, younger than 1 gigayear based on isochrone ages that we would determine through that analysis could definitely add planets. Just looking at the overall planet population around those stars and not making any sort of initial, and being careful about the sorts of cuts that we make.
The postdoc timescale, how much do you think this can increase by?
So on postdoc timescale, I'm hoping that we could roughly increase the number. If we just say we're doubling the number of planets that we would be looking at with K2 and TESS, and assuming roughly similar to the number that we see in the Kepler sample, then we would end up doubling the number of planets in both the old and young planet samples that we're looking at here.
Okay, let me ask and go to Zoom land whether there are any questions online that Travis could answer. Kurt, are you there? So give us a yes or no whether there are questions.
I'm here, and so far no questions. If someone wants to raise their hand, I will open the question and Q&A.
Okay, we'll give the online crowd a bit more time. We have a question in the back, yeah.
So when you showed the plot of the Neptunian desert, you highlighted these points that had always been in the desert, but there were a bunch of points that seemed like they also resided in that region that weren't highlighted. I was just wondering.
Yeah, so let me go back to that plot here real quick.
You can repeat the question for the online.
Yeah, can you repeat it, please?
So you highlighted these 9 points, but it seems like there's many other points kind of that are even more extreme, possibly.
Yeah. So sorry, I didn't go into the details of that. So those are candidate planets, so they aren't necessarily confirmed. So the difference between the planets that I've circled and some of the planets that you see are, for instance, in this region of the diagram, these are candidate planets. So I didn't necessarily want to assume that they were bona fide planets.
Yes, Aaron.
So on the HR diagram, you showed different regions where different dating techniques are effective, and there's a significant amount of overlap. Even assuming that some are more effective in certain age brackets than others, when the techniques do overlap, do you find close agreement? Do you find disagreement? And if you do, how do you decide which technique is being?
So that is going to be a large portion of the sort of work that I plan to do during my postdoc. This isn't something that I've had a chance to look into in a great amount of detail yet, but finding situations where ages are, in agreement, those are obviously going to be the easy cases, but part of the reason why I had some stars that I followed up with my thesis sample is because, for instance, there were some planets or some stars that had somewhat contradicting, either they had what appeared to be fast rotation periods, but then didn't have UV excess or something like that. Those were ones that we followed up with AO imaging or super ACS spectroscopy. And so I've got that information for those guys. Thanks. Yeah.
Yes, Mike.
Hey, for these low incident flux, overly large Jupiters that you highlighted, you have a sample of, I guess, several thousand planets. Isn't it possible that they're just statistical fluctuations? In a large enough sample of objects, some of the measurements are, are bad, and therefore lie above the line.
Yeah. So that's always a possibility. I mean, again, you'll notice that, like, at least based on the uncertainties that we place on those planets, there's obviously with the sort of updated information that we have with Gaia DR2, this allows us to get more concise constraints on things such as, for instance, the mean stellar densities, which will then inform future planet transit fitting pipelines. So that sort of stuff, we would expect those statistical fluctuations if we did, an improvement of that sort of analysis. We'd expect those to be much smaller in that case. Now, Kepler 706b, the one that I really hit on, it does appear to have a binary companion, which could be changing the isochrone age that we determined for that system, but then also it's going to require, additional analysis based on the sort of like mean stellar density analysis and using that to inform the planet transit fitting. And for instance, that planet's radius, even though the uncertainties associated with it might place it significantly above, it might also, we're not taking into account potential systematic effects, right? So we also have to consider those, at least based on the planet radius uncertainties. I guess when you're talking about a sample that's that large, you might expect to find a few, but not like, I guess, confirmed planets, which technically Kepler 706b is a validated planet, which doesn't necessarily mean that it's necessarily like 100% because it's around a relatively dim star that would be very difficult to do. And it's on a longer-ish orbit, so determining, for instance, an actual mass of that planet is going to be pretty difficult. So, yeah.
Okay, let's give it one more try online. Kurt, any questions that Josh
No,
can answer? Last call.
It's pretty quiet.
Okay. All right, last call in the audience here before we wrap it up. Okay, looks like we're right on time, so let's give Travis one more round of applause.